We're going to talk about multiple representations, but it's not going to be multiple reps that we move into technologies. We're going to sort of blend them. But we'll start off with just a few examples about representations. And I really want you guys to tell us about it first. And I'll see if my new tablet works. So, how are mathematical ideas represented in school math?
Or science. We won't discriminate. Even though we're math people.
We'll do math first inside.
Yeah, we're gonna.
I mean, you don't see mathematics. Something's in your head. You see examples of how it's used. But how is it represented?
Numbers.
What was that?
Symbolically.
Okay, symbolically.
And I also heard an N word.
Numbers.
Numbers.
School math. It's isolated.
The nice N word.
I can't write on this thing. Well, numbers, symbols. How else?
Typically more in isolation.
Hmm?
More in isolation instead of context.
Okay, that's where. It is in isolation. But how is it represented, even if it's in context or isolated?
Graphic.
Graphs. Anything else? Manipulatives. I hit the wrong button.
Watching Joe learn a new technology.
Well, you know, I need to fold this thing up and do it this way, but with the keyboard, I don't know what I did hitting this button, but anyway, manipulatives. Okay. Anything else?
Pictures.
I want to get rid of something. Here we go. Manips, okay?
Pictures.
Pictures.
Shapes.
So what do we typically do in school? We do all of those? Do we spend most time on one or more? A lot of it in elementary school is numbers. Right? There's some symbols, some graphs, some manipulatives. High school is largely symbols. Right? Kids figure out, or don't figure out in many cases, the rules for moving X's and Y's up and down and across. We do some graphs. But one of the big problems is kids sometimes learn these representations in isolation, meaning they don't know how certain numbers get connected to symbols, get connected to graphs. You know, years ago, back in the 70s, there was a big movement on using manipulatives to teach math, and it wasn't very helpful because the kids learned things with manipulatives, but they didn't see how some of those things actually came into play when they were dealing with symbols and graphs. There was that separation. So the biggest problem we have is kids sort of creating good ways to link these representations. So technology can be used to help us get through that. All right, so we're going to give you a couple of examples. I want to get rid of this thing. How's that? Will that do it?
Joe, another representation that sometimes I think kids struggle with, it's represented in words.
Words. Words. Verbal representations. A lot of kids ignore the verbal representations, meaning they don't read the math textbook, which is largely filled with I didn't want to. Okay, all right, so we're going to give you a couple of ideas about multiple reps, just to give you a quick overview. That it's something that goes from elementary school through graduate level mathematics. So it's not just a school thing. This is an Excel spreadsheet that helps kids see the relationship between different types of symbols, and numbers, fractions, decimals, percentages, but they could also see a fraction or a decimal in a graph. Okay, this was created by one of my students a couple of years ago who was out in one of your local schools, and she was sitting in there and heard two kids talking. They had recently gotten a vocabulary test back, and one student had something like 14 out of 15, and the other one came in late, only did 12 of the questions. He got 11 out of 12. And they had a different percentage correct on the test. And the two kids were confused. And one of them raised a hand and said to the teacher, we both got one wrong, but we have a different percentage. So this student came to me and said, how can I show that? And I said, well, why don't you show it correctly? So she created an earlier version of Excel to show this. I have two, so you can compare. You can change the numerator, the denominator, and see how one affects the other, and so on. It's just a different representation for something very, very sort of elementary and middle schoolish, but you usually don't think of it in terms of something like this. So you could put the 14 out of 15, and you could put the 11 out of 12, but you can see that the decimals are different, and you can see that the area is different. So this is a figure, a ratio, and a decimal. Right? So it's elementary, middle school example. But you can see there's two representations. They're linked, so kids see the numerator is going up, what happens to the graph? The denominator is going up, what happens to the graph? Because a lot of kids don't have a good feel for that. But when they're playing with this, it starts to give them an image in their head, which we refer to a concept image. Concept image is how a kid thinks about a math or science concept. And the image is really a collection of all the representations that they associate with that idea. So their concept image of fraction may change just by spending 10 minutes with this, because now they can bring that visual to bear in certain kinds of tasks. In our methods class, we teach our pre-service teachers how to create this. It takes all of what, 10 minutes to create it?
Maybe 15, if you can't find the correct buttons.
Right, it takes longer now because the new version of Excel has hidden the scroll bar. But we want our teachers, our pre-service teachers, secondary, to know how to do this so they can create these things on the fly when they need them. So there's one. So let me now ask you. Now let's go to high school. What's a sign? High school math. Sine of X, sine of 30. What is a sign?
You've all graduated.
The ratio,
It's a ratio of?
opposite, in the triangle, the opposite over the opposite length of the triangle over the hypotenuse, right?
Right, Tiffany. Okay.
I teach 6th grade, think.
Yeah.
And it's a curve, the sine curve, right?
Oh, perfect. You answered both questions. You answered the second question before I asked it. Okay? It's a sine, opposite over hypotenuse. Remember all that stuff? Right?
Yes.
Now, they start teaching this in 8th grade, don't they? Whether? I know some of the kids in the contact class, they get this in the 6th grade. It's opposite over hypotenuse. What's a sine wave?
The curve, or it's a periodic trigonometric function.
And what does it look like?
Okay, now this is interesting. Most people can't say what it is, but they do this. Now, where I ask everybody, that's a sine wave. So my question is, what does this have to do with that? They're both called sine. One is the middle school early algebra version on the left, and the next one is the trigonometry pre-calculus version on the right. kids think of them as two separate things, but they're both spelled S-I-N-E, and both are abbreviated S-I-N. What's the connection? Well, we'll show a representation. All right, notice in the triangle, in the circle, you see that triangle? There's the sign. All right, sign is 0.43. So we have a figure, we have an A over C, we have an algebraic ratio, and we have all the numbers, 3 representations. But if we look at the height of the red opposite, and we trace that, that's the green arc, look what happens. The opposite goes up to 1, and then what does the opposite do after that? You see the opposite is now starting to come down. Then the opposite goes below the axis. So, simple idea. There's one triangular representation, but the technology made it easy for us to link it to the curved representation. So students, 10th, 11th grade, get a sense that this early sign they learned is really the same thing as the sign they learned in math. So that's a high school example. So let's do another one. Look at this one. This is actually more math analysis. Those of you who are math majors probably got this in your 3rd year as a math major. Look at that definition. Can anybody make sense out of that definition?
Can anybody read that definition?
That's a standard definition you learn in advanced calculus. Every math major gets it. Most have no idea what it means. We did a study a couple of years ago where we had math majors who finished the course where they learned all of this and passed it. And a semester to a year later, we interviewed them to explain it. Most couldn't. They couldn't remember it. When we showed the definition, they couldn't explain it. They had no idea what it was after a 45-hour semester-long course. But then we created a sketchpad sketch that basically illustrated what it meant. And they played with this for 1 hour. You see there's 7 tabs, so there's 7 graphs, and then there's another one that has a different set of graphs. And in 1 hour, they understood it very well. And we tested them 2 weeks later, and they understood it very well. And then I tested them a year and a half later, and they understood it very well. They learned more in that 1 hour than they did with a whole semester with my colleagues across the street. Why? They had this visual representation now in their heads. So a year and a half later, when I asked them questions about it, they kept referring to, well, I remember sliding the epsilon slider, and I had to move the n over. They remembered these things from the visualization. Next year, I'm going to test this out in one of our 300-level math classes to see if using this kind of representation will help them learn it the first time around rather than a year later. So the main idea is to take symbols, numbers, in this case words that were really not understandable to most people, diagrams, and try to use the technology to help kids sort of make links between these representations. Because to really understand a math idea or a science idea, they should understand how it works numerically, how it works sort of conceptually, with diagrams, with models, with simulations, and see how these things are linked together. So that's what we're going to focus on.